So let's now formulate the zeroth law of thermodynamics. So why is it called the zeroth law? Does anyone know? Why is it not the first?
Came after first and second
It
law?
was formulated after the third law. It was more
Exactly.
fundamental.
Yeah. So if Nahi now comes up with another law, which is even more fundamental, what will it be called?
Minus first law.
-1.
Very good. Yeah. Yes. And if I come up with a law, it'll be called the imaginary law. All right. So the zeroth law. You all know this law, but let me just say it anyway. It's about transitivity of equilibrium. So if two systems, if two systems, A and B, are in equilibrium with a third system, C, then A and B are in equilibrium with each other, okay? So this is the zeroth law of thermodynamics. So the zeroth law of thermodynamics essentially is saying there is a useful quantity called temperature. Do you guys know how to show this? How the idea of temperature is encoded in this law? Have you seen this?
It's the speeds of the molecules.
That would be, yes, that would be a statistical mechanical point of view.
Classically, no.
But we are taking an agnostic point of view. We don't know that molecules exist, right? We are doing.
Hello.
Hello.
Can you hear me?
Yes, we can hear you. Is that Rafi? Yes, we can hear you. Okay. Let me say. Yes. Okay, Farhan. Yeah. Okay. Okay, anyone else wants to go? Yeah, so you guys, I'm assuming you are not familiar with the way how temperature comes out of this.
In zeroth law, we are just saying that there exists a quantity that would lead us to justify whether things are in equilibrium, and we're calling it temperature. Probably.
Yeah. Can you derive that?
Oh, no.
Okay, so let's do the derivation, okay? Okay, so we are going to do the derivation. So, so we are first assuming that A and C are in equilibrium, right? So we are assuming that A and C are in equilibrium. Now A is specified by, say, the value of pressure, but say P1, and this V1, the volume. And C is, say, P3, V3. Now, if they were not in equilibrium, there would not be any relationship between these quantities, right? Now, because they are in equilibrium, there must be a relationship between these quantities. We don't know what that relationship is, but there must be one.
So I had just a logical confusion here. So saying that they are in equilibrium implies that they have a relationship, but if they do have a relationship, won't imply that they have an equilibrium in general, will it, sir?
Right. Yeah.
I
Probably.
see. Okay.
Yeah. But that they may have a relationship which is not relevant here.
Okay.
But yeah, I haven't. Yeah. Okay. So let's look at. So let's call that relationship F. And the F has lots of arguments. One of the argument is what are the systems A and C, and the first is the pressure of the first system, the volume of the first system, and the second is the pressure of the second system and the volume of the second system. So this is the relationship, okay? Now we can solve this relationship because this is one constraint, right? This is one constraint for 4 quantities. So we can solve this to give us, say, one of the quantities in terms of the other. So let's choose that to be V3, the volume of C. So the volume of C expressed in terms of the other quantities, let's call that small f AC to specify the system. And it's going to have P1, V1, and P3. So this is a solution to this constraint equation. Okay. So similarly, we know that we also know that B is in equilibrium with C. And let's call the variable of B to be the values of the variable P2, V2, and this is already P3 and V3. And because they're in equilibrium, we have another relationship, which is F of BC, and then say P2, V2, P3, V30. Now we can also solve this to get V3. And we will get F, B of C. Here we will get P2, V2, and here we will get P3. So we get 2 different expressions for V3. So we can equate them. So we equate, so we have F of A of C with its argument P1, V1, and P3, and that's equal to F of B and C, and that has P2, V2, P3. Now, according to the third law, sorry, not the third law, the Zeroth law, because A and B must also be in thermal equilibrium, right? So it must be that according to the third Zeroth law tells us, so Zeroth law is a law of physics. We're not proving it. We are just using it to find its consequence. It's telling us that if I take, there must be a relationship such as this. Okay. Right. So this is also a relationship, involving the same variables. Well, with the P3 extra. So that means that if they are the same relationship, then the P3 dependence from this equation must drop out. That means that the P3 dependence in this equation must come as a multiplication on both sides. Therefore, this equation, from this equation, we should be able to derive an equation which is independent of P3, which is this equation. But it must be that this comes with P3 like an overall multiplicative factor. So we will end up with a relationship which I call theta A, P1, V1. I'm not dropping the C because there's no 3 dependence here, equal to theta B, P2, V2. Okay. So thermal equilibrium between A and B means that A and B has a quantity called theta, which is a function of the fundamental variables state variables P and V, and that they are equal. And this object, this theta, which is a function of P and V, which has to be equal, which is equal when things are in thermal equilibrium, we call it the temperature. Okay? So this is the definition of temperature, and this is called the equation of state. So why we define temperature to be this, but not say the square root of this, is a discussion we are going to have another day. But this equation of state will be different for different kinds of systems. So experimentally, one can show that for the ideal gas, the temperature is related to pressure and the volume through this relationship. Okay? So any questions so far?
Sir, I didn't understand the argument you came into. You're using theta A equals theta B.
Right. So theta A, and essentially what I'm saying is that this equation, you have here is nothing but this equal to this with P3 multiplied on both sides.
Oh yes, I just didn't get it. Why would P3 come out as a multiplicative factor here?
Because we are assuming there's only one relationship between A and B when they're in equilibrium, and that relationship is this relationship. But that relationship is also this relationship. But this relationship tells us that there is no P3 dependence. So if there is a P3 dependence, it must be in this form.
I see.
Okay.